Okay, in order for us to begin to talk about trees, we first need to talk about this subject called recursion. Okay, so a recursive function is a function that calls itself. So here's an example of a recursive function. Let's look at a similar version here in the compiler. Okay, so we're in main. We're going to print out this beginning statement, and we're going to call recurse. And then we have this printout to say recurse is complete. So I want you to look at this code and maybe pause the video right now and try and guess what's going to be displayed on the screen if I were to run this program. Okay, so think about it, look at the code, pause, and then come back in a second. Okay, so let's run the program and see what happens. Okay, so you'll see the introductory cout inside main about to call recurse, but then we see nothing else. And we get this pop-up that says our program has stopped working. Okay. So this might be a little bit unexpected. I'm sure you probably all guessed that we would never see this on the screen. Because when the flow of control gets here, we're going to call the function called recurse. And then the one and only thing we do inside here is call recurse again. Right, so this looks like it's kind of an infinite loop. Okay. But this is not exactly the same as an infinite loop. This is an example of infinite recursion. And we know from, we've all written infinite loops before, the program never crashes when that happens. It just kind of just runs forever. Okay, this program crashed, though, for a very good reason. Every time a function is called, this thing called a stack frame is added to the call stack. Now a stack frame holds the return address the program should jump to when the function is complete, and the stack frame also stores local variables and parameters that are passed into the function. We've talked about that before. The problem here is we have a finite amount of room on the call stack. Okay, so remember earlier we talked about every running program being this thing called a process image. Right, when we were talking about dynamic memory, we said, well, there's a text section, that's where the compiled code goes. There's a data section, that's where global data goes. We have the stack section. We have the heap. That's what we use for dynamic memory. And then we have this thing called a process control block, which holds all kinds of accounting information about the running process. Let's kind of blow up this stack portion of the process image. And every single time we call a function, we create this thing called a stack frame, and we push it on the stack. So what's happening here is, in an infinitely recursive function, we're basically going to run out of room in this stack space. So there's a finite amount of room here. If we ever fill the call stack, some operating systems will allow it to get a little bit bigger. So it might ask the operating system to make room for a little bit more space for the stack. But it will not allow, the operating system will not allow a single process image to consume all of memory. So here's my recurse program. I can't gobble up all memory that exists in the computer. That's one of the things the operating system does. It says, all right, you program, you're asking for too much memory. For the sake of the other running processes in the system, we're going to kill you. And that's exactly what happened. Okay, so infinite recursion is as bad as an infinite loop. Right? They both lead to these problems. With infinite recursion, though, our programs tend to crash when the stack part of our process image fills up. With an infinite loop, because it's not really allocating any resources other than the processor, it just kind of runs forever. Okay, now the value of a recursive function is that some problems are actually best solved by first solving a smaller version of itself. Okay, so let's look at the factorial problem. We all remember factorials, right? So 5 factorial is 5 times 4 times 3 times 2 times 1, or 120. Another way to think about 5 factorial is it's really just 5 times 4 factorial. And 4 factorial is really just 4 times 3 factorial, and so on. So we're framing the problem in terms of a smaller version of itself. We are going to perform this calculation on multiplication, but first we ask a recursive function to find a smaller version of the original problem. So 5 factorial is going to be 5 times the result of calling a function to find 4 factorial. Okay, so whenever we do this, whenever we recursively call a function, in order to avoid the infinite recursion we saw in recurse, that's definitely something we want to avoid, we need this thing called a base case. A base case is needed in all recursive algorithms. A base case is one where the problem basically shrinks to the point where there is no need to recursively look any further. In this case, 1 factorial is defined not to be a smaller version of itself. Instead, it's just defined as being the hard-coded number 1. All other positive factorial numbers can be defined as the product of the number and a smaller version of itself, except 1 factorial. That is the base case. So without a base case, we would have an infinite recursion problem like we did with recurse. But since we are defining this one special base case, we can write a factorial function that is recursive. Okay, so let me show you a recursive factorial function. And you'll see this is actually pretty simple, pretty straightforward. So we're going to pass in a number. We have a return value that's eventually going to be returned. And we're going to look for our base case. We always look for the base case. And we're going to say, is the number that got passed in, is that equal to 1? If so, we're going to set our return value equal to 1. But if the value that got passed in is not the base case, then it's the general case. And to solve the general case, we're going to use recursion. So we said we're going to take the number that got passed in and then ask the function to find a smaller version of itself. So we're in the factorial function, we're going to call factorial again, this time passing in num minus 1. That's when num is equal to 5, this is like saying 5 times 4 factorial. Okay, and then what's going to happen in that case, 4 is not equal to 1, so we're going to say 4 times 3 factorial. And that's going to come down here, and we are going to recurse until we get to the point when we pass in the number 1. Right? When we return 1, then we're going to return that value 1, and the flow of control is going to return right back to this point, and we're going to take the number and multiply it by the result, in this case 1. And then we're going to return to where that function was called, and we're going to repeat this process over and over again. Okay, so let's take a look at the call stack as we call the factorial function. Actually, let me run it first. So let me create a number variable, and we'll put the value 5 in there. Okay, so just declared a variable here, and then we're going to call factorial. It says 5 factorial is 120, 4 factorial should be 24, okay. 6 factorial should be 6 times 120, which is 720. Okay, so I feel pretty good that my factorial function works. Again, let's look at the call stack. Okay, so remember I talked about that the call stack and this thing called a stack frame. The stack frame determines what gets passed in, and any local variables are also stored on the stack frame. So we have this stack frame with num and retval. Every time we call the function, one of these stack frames is going to get pushed onto the call stack. Okay, so when somebody calls the factorial function, passes in the value 5, this is what the call stack is going to look like. So it starts with the first call to factorial. Okay, we have num is the parameter that gets passed in. Return value is a local variable. Let me show that code again real quick. Num is the parameter. Retval is what we're eventually going to return. It's just a local variable. Okay, and all we know right now is that num is equal to 5. Let's see if I can get these both on the screen. Okay, so when we call factorial from main with the value 5, num is going to hold the value 5, and the return value we don't quite know yet, right? Because when we get here, we say, is num equal to 1? No, 5 is not equal to 1. So we're going to go down here and say num times, and then we're going to call factorial again. This time passing num minus 1. So now our call stack is going to look like this. There's going to be 2 stack frames on the call stack. The original with 5, and now we're calling factorial again. Right. But now 4 is not equal to 1 either, so we're going to take 4 times factorial of num minus 1. It's going to make it 3. Okay, and our call stack is going to look like this. Okay, and so on. Again, we don't really know what's in return value yet, because as soon as we try and set something equal to that, we have to call factorial again. So let me do this one more time here, because we're going to get to our base case now. Okay, and then let me widen this a little bit. Okay, so when we get to this point when the number that gets passed in is 1, we know we're going to return the value 1. Okay, and whenever we return from a function, right, so we set our ret value equal to 1, we skip the else, and we return that value to wherever this function was called. Right, we know that where that function was called right here, and we're going to take the old value num, which was 2, and multiply it by the return value. 2 times 1 is 2. Okay, and for the first time, we've actually set a return value in the else. We had 2, this returned 1, 2 times 1 is 2. Now we're going to return that value to where this function was called. And we know exactly where that was called because we're going to pop the stack and return that return value of 2. And we're going to take the value that was on that particular stack frame, 3, and multiply it by 2. 3 times 2 is 6. We're going to return that value to where that function was called. 6 times 4 is 24. We're going to return to where that function was called. We're going to take 5 times 24. That's going to be 120. And then we're going to get to the end of factorial one last time and return 120. This time, that's going to be returned to main. And this is where we're going to print out that 5 factorial is actually the value 20. Okay, so that's a recursive solution to finding a factorial. It's not the only solution, but that's a pretty standard example of recursion. And notice it is really quite simple. We're just checking, is this the base case? And if so, returning something. Otherwise, we're doing some small calculation with a smaller version of itself. That's kind of the hallmark of these recursive algorithms. Okay, so let's look at another example. Let's look at the Fibonacci numbers. So you might remember seeing these somewhere in your studies. The top rows are the actual Fibonacci numbers themselves, where the bottom row numbers just indicates which Fibonacci number we're talking about. Okay, so if I said, tell me what the the 8th Fibonacci number is. That means go to the index at position 8. Fib 4, Fib 0. So we could just look at our chart here and say, well, Fib 8 looks like the value associated with the 8th Fibonacci number is 21. And Fib 4, that's the 4th value here. It looks like the number that we should return is equal to 3. And Fib 0, if we go here, we see Fib 0 is 0. So what do these Fibonacci numbers mean? Well, you probably have seen these before. You can get any Fibonacci number by basically taking the sum of the previous two numbers. So let's go back to Fib 8, 21. How did we get 21? Well, we just took the value 8 and added it to 13. Okay, so if we're looking for this number, we go back to and sum those two numbers together. Okay, so one way of thinking about this is we could say, well, Fib 8 is really 8 plus 13, which is 21. Or another way of saying it is, well, Fib 8 is really the sum of Fib 6 plus Fib 7. Right, so Fib 6 we know is 8, Fib 7 is 13, based on our little chart here. 6 and 7 were 8 and 13, and if we sum those two together, we get 21. Okay, so really what we're doing is we're defining a Fibonacci number by calculating the sum of the two smaller versions of itself. So we can come up with a base case and a general case for the Fibonacci numbers. Okay, so Fib 0 is always going to be 0. Fib 1 will always be 1. These are the base cases. Okay, and then the general case, we'll say Fib n is always equal to Fib of n minus 2 plus Fib of n minus 1. Okay, and this is our one general case. So let's look at some code. So we're done with factorial. Let's look at a recursive Fibonacci function. Okay, so it's called recursive fib. We're passing in a number that's the index in this chart here. So if we want the second Fibonacci number, we'll pass in 2, and we're expecting to get a 1. If we say fib of 8, we're expecting the function to return the value 21. So that's what num is. We have our return value. Here we're checking our base cases. Is the number passed in equal to 0? If so, we'll return 0. Otherwise, is the number that gets passed in 1? In that case, we'll set 1 to be our return value. If neither of those are true, that means we have the general case, and we'll set the return value equal to be the sum of calling recursive fib, taking num minus 2, and then doing a little bit of math here. We're going to add that to the result of calling recursive fib and passing in num minus 1. Okay, so let's run this a few times and see what we get. So I'll just use the reuse this code up in the driver. Okay, so we'll say fib of some number is equal to this. Okay, and we'll start at 0. So fib 0 should give us 0. Fib 1 should give us 1. Let's see here. Let's try, I don't know, fib 4 should give us the value 3. Okay, and then we know fib 8 should give us 21. And let's just do one more. Fib 9. Fib 9 should give us 34. Okay, and again, I won't redraw the call stack, but remember, every time you call a function, it pushes the stack frame on the call stack, and eventually the stack frame is popped, and you go to exactly where the functions were called. Now here, notice there's 2 recursive calls in each one of the general cases. Okay, so let me put some bigger numbers in here. So maybe fib 20. So fib 20 is 67, 65. Let's try fib 30. Okay, fib 30 is a nice big number. Fib 40. Okay. Notice for the first time we're not getting an answer back instantly. Okay. It's actually taking quite a bit of time here. It does come up with an answer. Okay, fib 40 is this value here. Okay. Let's try fib 50. And I think we're going to be here for quite a while. I had this running for quite a long time before, and it didn't finish in the... I had to wait, a good 10 minutes, and it still didn't finish. Okay, so let's try and figure out why, or what's going on here. Maybe I'll let this run while I draw this picture. Let's go back and see exactly what's happening when we called fib of 5. Okay, well, fib of 5 really results in two recursive calls. We're going to take fib 3 and add that to the result of calling fib 4. Right? But calling fib 3, that results in two more recursive calls. So we'd have to say fib 1 plus fib 2. Now, fib 1 that's a base case, so there aren't going to be any more recursive calls. But fib 2 is not a base case. So this would return fib 0 plus fib 1. Okay, these are also base cases, so we're just going to return back up here, and then the call to fib 4, well, that's not a base case, so this is going to result in call to fib 2 plus fib 3. Neither of these are base cases. This will be fib 0 plus fib 1. Okay, these two are base cases, but fib 3 is not. So this would be fib 1 plus fib 2. That's a base case, but this one is not. This would be fib 0 plus fib 1. Okay, so there were a lot of function calls there. And as 5 is a pretty small number, and you'll see that we had quite a few function calls. If I called fib 6, you could probably imagine we're going to have, an even bigger tree, right? Because fib 6 will really be this plus another set of calls, basically everything that's right here, fib 4 plus fib 5. So that would be, we're almost doubling the number of function calls that we have to make each time. And whenever we have this doubling behavior, the numbers can get big very, very quickly. So when we get to fib 50, okay, we are just have a huge number of functions to call. There are an incredible number of calls when num is large. Now the call stack never has more than the height of this tree in stack frames on it, but there are so many calls that it literally might take days for all of them to complete. And in fact, we could go and see, is this program done yet? Nope, it's still running. And again, I think it might be running all day just because we doubled just 10 more times, but that is a huge increase in the number of function calls. So every call requires a little bit of work. We have to create the stack frame, we have to push it on the stack, and then when the function's done, we have to pop the stack. That doesn't take a whole lot of time, but we're doing this so many times that it really adds up. Now, of course, there are more efficient ways to do Fibonacci numbers. I'm going to kill this. And let's look at a solution to Fibonacci that uses iteration rather than recursion, which in this case is much better. Okay, so the function's called loop fib. And basically we start with our first two Fibonacci numbers, 0 and 1, and then for all the rest of the numbers, again, we're going to pass in what number we're looking for. We're basically going to copy the second into the first and sum them together. Okay, and then make a copy. After this loop iterates, num1 is supposed to hold the Fibonacci number that we're looking for. Okay, so let's go back and let's start a little bit smaller here. So fib 0 should give us 0. Fib 1 should give us 1. Fib 4 will give us 3. Fib 8 gives us 21. Fib 9 should give us 34. Now, because we're using iteration instead of recursion, Fib 20 is 67, 65. It only took 20 iterations of the loop to find that value. Fib 30, again, basically happened instantly. Fib 40, remember we had to wait a few seconds to get that one with a recursive solution. Well, now we get it instantly. And Fib 50, I think this number is so big that I think we're going to have some kind of an overflow. So we definitely shouldn't have a negative number, but that's because the numbers got so big that the answer actually couldn't fit inside a plain old integer. So it overflowed, it wrapped around. But the amount of time it took to execute was basically just 50 iterations of this loop, which we know could happen basically instantly, well under even a fraction of a second. Okay, so this particular solution, the Fibonacci numbers, was easy to solve with an iterative approach. With many problems, the most straightforward way is going to be to use a recursive algorithm. And soon we're going to be talking about trees, and almost everything we do with trees, it will be easier to use a recursive algorithm than an iterative one. It'll just be easier to think of an algorithm that's recursive when we talk about trees. So that's eventually what we're headed for. And we're going to talk about a few more examples of recursion before we get to the trees.